One theoretical problem we can be presented with regarding proton NMR would be what compound with a given formula would produce only one signal, specifically a singlet, in the proton NMR. Now here are three different formulas, and what we want to do is imagine a structure where all of the hydrogens are chemically equivalent. These can be quite difficult in the beginning, and it helps us to see a few examples and learn the tricks in order to help figure them out. And you can start by trying to imagine what compounds might have a given structure, and then slowly refine your structure to try to make more and more hydrogens equivalent. If you'd like to, pause the video here and see if you can come up with a couple of structures that fit each formula and see if they make sense. You can also use the chemical shifts that are given to help figure out or help make a guess as to what structure you're looking at. And you can also use the index of hydrogen deficiency to get an idea whether there are rings or double bonds present. If we consider the first example and consider what the formula would look like if we had only a fully saturated compound with no pi bonds present, we would expect to have double the number of carbons plus 2 for hydrogens. So with 6 carbons times 2 is 12 plus 2 is 14. We notice with C6H12 we're missing 2 H's, which gives us an IHD of 1. This means that we have either a ring or a pi bond. And if we imagine a 6-membered ring, that would give us the right formula, because each of these carbons in the ring is going to have 2 hydrogens. And then we also realize, because of the symmetry of the ring, that all the hydrogens are equivalent. And so one way to get one trick, so to speak, of getting all the hydrogens in a compound to be the same is to have a ring. Now it's also worth noting that if we had started with a double bond here, if we put this at the end of a 6-carbon chain, then we're going to have a bunch of non-equivalent hydrogens. Because although the 3 at the end will be the same, the CH2 next to them will be different. The CH2 further in is closer to the alkene. This CH2 is allylic and will be therefore even further deshielded. And of course the 3 vinyl hydrogens, all of which are distinctly different, would produce additional signals as well. What we can do, however, to make hydrogens equivalent would be, instead of having a chain, to put a pair of methyl groups on the allylic position. So we have 6 hydrogens to be the same, that's half of them. And this is the other primary trick to getting a bunch of carbons or a bunch of hydrogens to be equivalent, is to have a bunch of methyl groups. And with 12 hydrogens, we'd need 4 methyl groups. If we have 4 methyl groups on an alkene, then that not only fits the formula, but they would all be equivalent. Now, given the chemical shift, that actually is going to tell us that our ring is a better answer, because the chemical shift of the allylic hydrogens in this particular example, 2,3-dimethyl 2-butene, are going to be a little bit further downfield, although that's not something you would be a distinction you would be expected to make at this point. And so either one of those would be valid answers. Now that we've seen 2 tricks, a ring and multiple equivalent methyl groups, to creating equivalency in hydrogens, Let's try or look at these two examples again. In this middle case, we see that with our formula, we have exactly the number of hydrogens we would expect in a fully saturated compound with no rings. So if we take 5 and double it, we get 10, add 2 is 12, that's how many we have. And so we have no ring and no pi bond. So if we're thinking of tricks for equivalence, what we want now are a bunch of CH3s. And if we think about 12, right, 3 goes into 12 4 times, we would need 4 CH3 groups. That's 4 out of our 5 carbons. And to make them all in the same molecule, we'd have to attach all 4 of the CH3s to the same carbon. And that structure, 2,2-dimethyl propane, would have 12 equivalent hydrogens, relatively far upfield, as there are no de-shielding groups, no electronegative groups, no pi bonds present in the molecule. The last example, our chemical shift, is going to be a big hint. 7.3 is very characteristic of an aromatic ring. And C6H6, of course, is the formula for benzene. And if we do our formula again with 6 carbons, we already saw we'd have 14 hydrogens. So this is an IHD. 8 hydrogens missing is an IHD of 4. And if we remember with a benzene ring, if we look at those individual pi bonds, we've got 1, 2, 3 pi bonds in a ring. So this structure fits our formula, and if we draw in the 6 hydrogens, 1 on each carbon, we realize, of course, that they're all going to be the same.